Right. In this video, we'll derive the equation of work done and its equation. So now, before we derive this equation in isothermal process of reversible process in a non-flow process and thermodynamic kind. So first of all, you need to understand this word isothermal process. If you happen to divide the weight iso and thermo, we're talking of heat, then iso meaning same one. So now isothermal process, it is the process, it is a process where temperature, the key word here is temperature, held or keep, or rather kept, according, I don't know the English which you can like to use it, held or kept constant. So the keyword there is constant and temperature. So temperature here is held constant in isothermal process. So now our interest here is work done and heat, finding the equation of these two equations. So now we all know that the general equation for work done, it is work done is equal to force times distance. Then this was manipulated to be work done is equal to the integral of pressure and change in volume, direct proportional to change in volume, which is all one and the same. This is because we're dealing with the thermodynamics, which is it. You're talking about it, thermodynamics. So this equation is all one and the same in a physical, mechanical performances and under thermodynamics. We are dealing with the properties, the microscopic properties of gas. We use this equation. So now this equation of work done and the other equation which I was talking about is for heat, which is change in internal energy is equal to heat applied minus work done. These are the equations which we will derive in. So now, in thermodynamics, every reversible process, when you want to determine the equations, you need to understand, number one, the first law of thermodynamic. What is the first law of thermodynamic? The first law of thermodynamic, it is this equation. This equation, it is the first law of thermodynamic. How do you state it? It states that the change in internal energy is equal to the heat added to the system minus the work done. This is the first law of thermodynamic, how it states. The change in internal energy is equal to the heat supplied, or rather applied to the system minus the work done. Then that is the first law of thermodynamic. So this first law of thermodynamic, it will help us to derive, rather to extract out the equation of work done and heat in this equation. So now, upon understanding the properties of thermodynamics, like we said earlier in previous videos, you need to understand, or rather to know each and every property of thermodynamics and the laws. So here we are talking of work done. So now we also need to talk about, since we're talking about gases, the behavior of particles, the movement of particles whenever it is applied at constant temperature. So let's not forget, rather to appreciate the ideal gases. Ideal gases. You can't talk of movement of particles without talking of ideal gases. You need to appreciate this law, ideal gases. When you talk of ideal gases or gas laws, ideal gases, these are gas laws, so to say. We have different kind of gas laws. We have Charles law, Bohr's law, Gay-Lewis gas law, a lot of laws. So now when you combine all these gas laws, they form what we call ideal gas law. Ideal gas law. Now, ideal gas law, it states that pressure and the product of volume is direct proportional to number of moles, the universal gas constant, and the temperature. So this is the gas law. So this is the equation. We're gonna use this equation on this equation. Yeah, this equation and this equation in order to extract or rather to derive the equation of work done. So these two equations are the equation we are going to use. So I'll name this equation as the equation 1 and this as the equation 2 so that it will be easy for us to understand what we're doing. So now let's start with this one. Since we are saying that temperature is held constant, remember, so when temperature is held constant, there is no change in temperature. So if there is no change in temperature, so whenever pressure there it is applied, the change in occupation of particles by the volume, it will also be the same. So here we are saying that this as it PV is equal to nRT, and so here we make P, pressure to be the subject of the formula, meaning the pressure is being applied, the heat to the system is being applied by force, meaning by pressure it is increasing. What for temperature to be lessened, there must be increase in pressure so that the particles are able to to move. So you're saying V, we make P to the subject here. So when P is the subject here, we cancel this. P is equal to nRT over V. So these are the product of P. P is equal to this. So when P is equal to this, we get this and substitute it into the first equation of work done, the chain equation of work done, which is equal to the integral P and change in what, which is the Vi, change in volume. So where is P? We substitute this. So we say W is equal to integral, where is P? We substitute nRT over V. N in number of moles, R universal gas constant, and T, which is temperature, over V, change in V. So here we say, believe me you, here we said that temperature is kept constant. So if temperature is kept constant in the internal heat energy of the system, which is this one, change in internal energy of the system one is equal to nRT. You need to know this equation where being taken from. So this is how it is. So now, since temperature is kept constant, there is no change in temperature. So temperature is zero. Even universal gas constant and number of moles will be equal to zero. So meaning there will be no change in temperature in isothermal is equal to zero, no change. So since it is equal to, so this we what remove it out from the integration. So how do we remove it out from integration? We don't just remove it out like magic, like we just remove them or rather we erase this part. No, we need to perform mathematics. So here we have to do like, since we go to this one, we just introduce a 1 over 1 here, then we say integral of nRT over V. Then this one will multiply by this one we place here. So we have nRT, then integral of V, dvi. So when we integrate this, we are saying we have in nRT integral of the natural logarithm of this we have in at in NV, in NVI. So here we have in NV, here we have final volume and initial volume. So this is how the work done equation is being transformed in isothermal process. So after having this as a in V as a natural logarithm, so here we say since it's a natural logarithm, so here we say W is equal to nRT upon it being a natural logarithm. So here we say nRT is equal to this one will be in xi, in V. So when this is like this, or final and initial. So final and initial, then this will be, when we interchange this, it will be W is equal to nRTI. Upon being a natural logarithm, we all know that so this one is more like in V final V initial Vi. So when it is like this, more like here we have A and here we have a B. So according to the nature of logarithm one, when you have in x a bi, this is same as in x a minus in x b. So which is in x a over in x b, which is a over b. Same applies to there. So we have work done is equal to nRT in V2 over V1, which is final volume over initial volume. So this is the equation of work done in isothermal process. Work done. So this is how we derive the equation of work done in isothermal process. So remember, when you're deriving the work done in isothermal, you need to have two equations, meaning the ideal gas equation and the work done equation itself in thermodynamics. So this is how the equation of work done is being performed. So this performance, the equation for it. So the equation for it here, it equation, since we have solved for work done, here it's for it equation. The it added to the system minus the work done as the first law of thermodynamics, which is the first law of thermodynamics, change in internal energy plus is equal to the it added to the system minus work done. So when you try to make this to be the subject of the formula, we have Q is equal to change in work done minus W. You see how it is. So now, after having this change in work done minus W, when we make Q as the subject of formula, since we want to find out the equation of it. So the equation of it is extracted from the first law of thermodynamics. So the first law of thermodynamics, it will give us the guide on how to derive the it equation under this process of isothermal. So now, so we just use this. So since work done is equal to number of moles, universal gas, and the what temperature in V2 over V1. If work done is equal to this, then where there is the work, we substitute this equation. So here we say Q is equal to change in U minus nRT in V2 over V1. After substituting this, then this change in U in isothermal, change in internal energy. In isothermal, change in internal energy. This one, change in internal energy. Final final internal energy minus initial internal energy. This in isothermal, it is equal to 0. This is why, because temperature is kept constant. When temperature is kept constant, even number of moles is 0. Even universal gas constant is 0. So these two features will multiply by 0 and they'll still have 0, which is PV is equal to 0, and this one is equal to U2 minus U1 is equal to 0 as well. So where is internal energy, we put 0. So Q is equal to, we just remain with nRT in, so you see, that's one and the same. This is how the equation of it is being derived. So here the many principle here, rather the only key feature here is knowing the first law of thermodynamic and the ideal gas law, meaning the gas law. You need to understand this. Then you'll be able to derive every equation in reversible process. So these are the equation of work done and heat equation in isothermal process.